All right, everyone. So this is a short video I want to make about a useful tool. I personally find this tool very useful, and when I'm teaching students or helping or tutoring them in programming and specifically mathematical programming, some problems with things like Project Euler, etc. This tool often comes in handy. What is this tool? So this is a piece of code that I just wrote here, and I want to go over it. What does this code do? This code converts a number from the decimal number system, from the decimal base system, to any other system, to any other number system. So, what is the problem here? The problem we're trying to address, and you'll excuse this drawing pad that I'm using. This is a unexpected stream that I want to do before I go get my morning coffee. So, what is the problem? The problem is the following. We have a number in the decimal system. What is the decimal system? The decimal system is a number system where our digits are the set 1, 2, 3, 4, all the way up to 9. Okay? These are all the digits we're allowed to use. So this is the regular number system we humans work with daily. So if you can say number 123, number 91. Notice the number 123 can be decomposed into, let's just give this a name. We'll call this base 10. And we, of course, forgot the digit 0. There we go. Now, what is base 10? So if a number is in base 10, also known as the decimal number system, then I can decompose it as a sum, so we can write this as a sum of multiples of powers of the base, which in our case is 10, right? So how does that work exactly? Let me pull this down. How do I rewrite 123 as a sum of multiples of powers of 10? Well, what is 123? 123 is 100 plus 20 plus 3. Now 100 is 1 times, that's my multiple. Now I need a power of 10. Well, luckily 100 is 10 squared plus. Now I need to rewrite 20 as a multiple of a power of 10. Well, 20 is 2 times 10 to the first power. Now I need to rewrite 3 as a multiple of a power of 10 plus 3 times 10 to the 0th power. And we're done. We've represented our number in the decimal system as a sum of multiples, of powers of the base. So sum, these pluses, multiples, these coefficients here, powers of the base. Now, notice that any number that exists in this decomposition, any digit that you see here, any number that is here, I'm talking about these coefficients. Every one of these coefficients that I've underscored has to lie in my set of digits. So it has to be here. These are the digits I'm allowed to use. Okay? These are the digits I'm allowed to use. No other digits. In other words, this multiple, for example, I can't put a 17 here. I could not have said 17 times 10 squared, for example, because 17 is not a digit in my number system. My digits are from 0 to 9. And so once I've decomposed my number into this sum, then what I can do is I can just conventionally say every digit, I can conventionally say ignore these powers of 10, just write the coefficients next to each other like so. And by convention, the rightmost term, the rightmost 3 here, will be the multiple of 10 to the 0th power. So this is the power of 0. The one to the left of it is the first power. The one to the right of it multiplies the base to the second power. So this is the convention. Notice this is just an easier way to write this. They're completely equivalent. We're just dropping the powers of the base. And by convention, we're saying this rightmost digit will represent the 0th power of the base. The digit to the left of it, the first power. The digit to the left of it, the second power, etc. Okay, fine. Now comes an analogy or an analogous question saying, okay, suppose I have a number 123, same number, but this time I'm going to say that this number is written in something called um, octal system, and we'll put an 8 here to signify that it's an octal system. What is the octal system? The octal number system is the number system where my digits are now from 0 to 7, right? The decimal, when this was a 10, we had digits from 0 to 9. If this is 8, my digits are from 0 to 7. So what is this number if my digits are from 0 to 7 and the base is 8? Well, what did we let's look at the analogy. What did we do above here? We took each digit of my number and we multiplied by the base to a power. The power started from 0 if we're looking at the rightmost digit and increased by 1 as we went to the left. Now we're going to do the same thing here. We're going to take each digit and we're going to multiply by the base to a power, where the power starts from 0 if we looked at the rightmost digit and increases by 1 as we go to the left. So this represents the 0th power, 2 represents the first power, 1 represents the second power. So this is 1 times 8 to the second power plus 2 times 8 to the first power plus 3 times 8 to the 0th power. This is my number. This number here, 123, written in octal system, represents this number in the decimal system. So I can convert from any system to the decimal system by writing the full expansion like so. Right? And we can see what this is. Of course, 8 squared is 64. 64 plus 16 is 80, and 80 plus 3 is 83. So this number is actually equal to 83. I hope I did that math right. Haven't had the coffee yet. All right. So this process is the same for any base. You give me any base you want, give me a number, let's say 4. For what shall we say, A3. And we'll say that this is in the hexadecimal system. Now, what is this A? Well, in the hexadecimal system, because the base is 16, my digits range from 0. This is my digits. These are going to be from 0 to 9. These are the regular decimal digits we know, but there are more of them. Now, if I can't just write 10 because that's not really a digit, that's 2 digits next to each other. I'd like it to be one sort of entity. We're getting some philosophical terms here, but instead of writing 10, people have decided to just write letters. So A, that represents my 10, B is my 11, C is my 12, D is my 13, E is my 14, F is my 15. Okay, so there are the digits in the hexadecimal system. Now, here I have a number, 4A3. I know it's in the hexadecimal system. I want to convert it to the decimal system. Well, let's do the same thing. How do we go from a base to the decimal base? Well, we just learned what we do, base 10. So what we do is we take each digit, we multiply it by the base to a power. What power? Power start from 0 if we look at the rightmost digit and increase by 1 as we go to the left. So this is going to be 4 times the base to the appropriate power plus A times, but remember, I'm going back to the decimal system. So what is A? Well, A is the 10 here, right? A is the 10. So I can say 10 times 16 to what power? This is first power plus 3 times 16 to the 0th power. Now notice this number is quite large. It is quite large, 16 squared. And I mean, if I put an extra digit here, that's going to go into third powers. So 16 to the third power can get quite large, but these large numbers are very concise in the hexadecimal system. And the hexadecimal system became incredibly powerful when we're dealing with the memory inside of a computer, when we want to look at certain addresses of the memory, because a computer today has a ton of memory slots. If we wrote the address of the specific slot in the decimal system, the number would be huge. But in the hexadecimal system, we can use less digits to address the same slot memory location. Okay, so this is essentially how we go. This is how we go from any number to base 10. Any a number in any base to the decimal system. Now the question becomes, how do we go in the other direction? If I give you a number in the decimal system, how do you go in the other direction? So suppose you have a number 13, and this is in the decimal system. This is the regular 13 we know. Now I'd like to write 13 in the binary system. What is the binary system? This is a system where my digits consist of the set of 0 and 1. That's all. Base is 2. Why 2? Because I only have 2 digits. Now, in this case, when you want to go from the decimal system to another system, the process is very simple. So what you do is you look at your base. Our base is 2. And you ask yourself, what is the highest power of the base that fits in my number? What is the highest power of 2 that can fit in 13? Well, that's 2 cubed, right? 8. 2 cubed. So third power of 2 is the highest power that will fit here. So we write that 0. We put a placeholder for the 0th power, first power, second power, third power. Right here, we put a 1. Okay? Now, so far we have 2 to the third power. That's 8. So far we've accounted for 8. What is remaining? Well, 13 minus 8 is 5. Right? 13 minus 8 is 5. This is my new number now. Now I ask myself the same question. This process repeats. What is the highest power of 2 that fits in 5? Well, it's the second power, right? 2 squared is 4. So that was our 0th power. That's our first power. That's our second power. I put a 1 here. So 2 squared, that's 4. That's what we counted for. So we had 5 minus the 4 we just had, and we have a 1. Same process again. What is the highest power of 2 that fits in 1? Well, that's 0, right? 2 to the 0th power is 1. So that's 0. That's the 0th place. I put a 1 there. Now, I had a 1. I just accounted for a 1. The answer is 0, which means I've represented the number that I started with completely in the binary system because I have nothing left. I have 0. I've accounted for everything. And so everything that is not a 1 in the binary system is a 0. Now, how do you check that you did this correctly? Well, we do what we did up here. We take this number in the binary system and we go into the decimal system. How did we do that? We said take each digit, multiply by the base to a power, and add them up. So let's take this digit. 1 times 2 to what power? Well, that's 0. That's the first power. That's the second power. That's the third power. So 2 cubed plus 1 times 2 squared plus 0 times 2 to the first power plus 1 times 2 to the 0th power. If I did this correctly, the result should be 13. 2 cubed is 8, plus 2 squared is 4, that's 12. 0 times anything is 0, plus 1 is 13 in the decimal system. So we did this correctly. Okay? Let's do this one more time. Let's say we have the number 15, or let's do 23. Okay, 23. And we want to go to the binary system. Remember, what is the binary? It has base 2, so digits 0 and 1. Now again, we ask ourselves, what is the highest power of 2 that fits in 23? Right? Well, that power is 4. That's 16. So highest power is 4. So we put our placeholders. 0th power, first power, second power, third power, fourth power. Right there, we put a 1. So we had 23 originally. We just got 16 because we raised 2 to the 4th power. What is our remainder? Our remainder is, of course, 7. So now we repeat this process. We ask the same thing of 7. We say, what is the highest power of 2 that fits in 7? And that's, of course, 2. 2. So 0, 1, 2. Put a 1 here. So we had a 7. We just accounted for second power of 2, which is 4. And we're left with a 3. Repeat the process. What is the highest power of 2 that fits in 3? That's, of course, 1. So that's 0th place. That's the first power right there. Put a 1. Let me bold this here. 1. So we had a 3. We just accounted for 2 to the first power, and we're left with 1. Repeat the process. What is the highest power of 2 that fits in 1? And that's the 0th power of 2. 0th power is right here. Put a 1 there. We had a 1. We just accounted for a 1. We get a 0. So we've accounted for the complete number 23 because we were left with a 0 at the end. Everything has been accounted for. So everything that's not a 1 is now a 0. Okay? So this is the process, and you can check yourself for practice. You can see that this number in binary is in fact 23. So just like we did up there. Okay, now there is one more step I want to cover before we go to before we dissect the code. Now the step that I want to cover is the following. What if instead of binary I want to go to the ternary base? What is the ternary base, you ask? Or just let's make it more interesting. Fifth, base 5. Base 5 is not as common as base 2 or the decimal system, but let's take 23. And this is in decimal, and let's try to go to base 5. What is base 5? We have digits 1, 2, 3, 4. These are my digits. I want to go to base 5 here. Now, same process repeats. What is the highest power of 5 that fits in 23? Well, the highest power of 5 that fits in 23 is, of course, 1, because 5 to the second power is 25. Now, remember that when we were doing this, when we were writing numbers as a sum of their powers of bases, we had these coefficients, right? These coefficients in front of the numbers, 1, 2, 3 here, etc. These coefficients are what we put here when we go to the system. In base 2, my only possible coefficients are 0 and 1, and that's what you see here, right? That's 1 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 to the 2, 0 times 2. These are my coefficients. So not only can I have power, not only do I need to look at the highest power of 5 that fits in 23, but I also have to ask myself, what is the coefficient of that power? The highest coefficient of that power. So the highest power of 5 that fits in 23 is 1. That's correct. So 5 to the 1 is 5. Now, what multiple of this? What is the highest multiple of this that will fit in 23? And that's, of course, 4. And that's, of course, 4, right? So since the highest power is 1, we put our placeholders just like before. That's the 0th power. That's the first power. But now we just said, what is the coefficient that will go in front of this first power? What is the highest multiple of this first power that fits in 23? And that was 4. So the number that I will put here is 4. And I'm allowed to do that because 4 is in my system. 4 is a digit in my system. I couldn't do that here in the binary system. I can't put a 4 there because 4 is not a digit. My only digits are 0 and 1. And it just so happens that in the binary system, you don't need to ask yourself what is the highest multiple of this power. Just looking at the powers, it will be enough to get you the right representation. It just nicely works out. But in general, if you're going to some general number system, you do need to ask yourself, what is the highest multiple of this power that fits in my number? So the highest multiple of the first power of 5 that fit in 23 was 4. So what is 4 times 5? And we're repeating this process. Look, we had 23. We just accounted for 4 times the first power of 5, which is 20. And we're left with 3. So now we ask ourselves the same question, just like above here. We say, what is the highest power of my base, 5, that fits in 3? And that's, of course, 0. Now, what multiple What is the highest multiple of that number that fits in 3? Well, 5 to the 0 is 1. 5, let me write this down. 5 to the 0, the highest power that fits in 3 is 0. Now 5 to the 0 is 1. What is the highest multiple of 1 that fits in 3? And that is 3. So the coefficient that I'm looking for here is 3. And I put that down. So what does this say? This says that if the number 23 in the decimal system, the regular 23 that we've looked at, is the number 43 in base 5. And we can check, just like before. How do we check? We take each digit, multiply by the base to the power. So 4 times 5 to the first power plus 3 times 5 to the 0th power. And you can see, of course, that this is 23. Let's do this one more time, and then we'll look at the code. So we're going to look at number 100 in decimal system, and our job is to go to base 3, ternary system. This is what it's called sometimes. So the same process. What is the highest power of 3 that fits in 100? Highest power of 3 that fits in there is 4, because 3 to the 4 is 81. Now let's put our placeholders. So that's 0, 1, 2, 3, 4. So I know I'm going to have some coefficient here, but what coefficient? Remember, this is base 3. My digits are 0, 1, and 2. My coefficient is allowed to be any one of these 3 numbers. What is the highest multiple of 81 that fits in 100? And that's just 181. So this coefficient here will be 1. Okay, so we had 100. We started with 100. We just accounted for an 81. So what are we left with? We're left with 19. Repeat the process. What is the highest power of 3 that fits in 19? And that is, of course, 2, I believe. I'm pretty sure it's 2. So it's 2. 3 squared is 9. And now I say, what is the highest multiple of this number that fits in 19? And that, of course, is 2 times 9. And that's fair game, because 2 is a digit in base 3. 2 times 9 is 18. It fits here. So this is the second power. So 0, 1, 2. And the coefficient we just said is 2. So we put 2 there. So we started with 19. We just accounted for 18, right? 2 times this number, and we're left with 1. Now, what is the highest power of 3 that fits in 1? And that's 0, 0th power. So the number that the place where I will put a digit will be right here in the rightmost placeholder. What should that digit be? What is the highest multiple of 1 that fits in 3? What is the highest multiple here that fits over here? So this is 3 to the 0, and that is, so I'm left with a 1, right? So what is the highest? So it's going to go into the 0th place. 3 to the 0th power is 1. So what is the highest multiple of 1 that fits in 1? And that's a 1, of course. So, and so everything else gets a 0, 0, 0. Let's check. This is base 3. So this becomes 1 times 3 to the 0th power plus 0 times 3 to the first power plus 2 times 3 to the second power plus 0 times 3 to the third power plus 1 times 3 to the fourth power. Now, 3 to the fourth is 81. 3 squared, that's 9. 9 times 2 is 19. What do we have here? So, yeah, 2 times, let's check. So this is 3 to the fourth power, 81, plus 2 times 3 squared. That's 18, not 19. 2 times 3 squared is 18. 9 times 2 is 18, plus 1 times 1. And this gives me 100, as expected. So this is our process. Now let's see how the code handles this. First of all, I need a way to ask myself, as you saw in this process, I kept asking, what is the highest power of the base that fits in the number? So I have to write some code that will give me a highest power of the highest power of a number that fits in some larger number. And if you know your algebra, you know that the mathematical function that gives me the power, the highest power, is logarithm. So I could say, if I want to know, if I write logarithm base 10 of 100, I know that's 2, right? Because the highest power of 10 that fits in 100 is 2. So this will be 2. If I write logarithm base 2 of 9, this will be 3 point something, because 2 cubed is 8, but this is a little larger than 8, so it'll be a little more than 3. But the highest power, the highest integer power of 2 that fits in 9 will still be 3. So what does this tell me? This tells me that if I'm getting some decimal out of this, which I will, if I'm getting some real number with numbers with digits after the decimal point, I want to discard them. Okay? I want to discard those digits. So I want to floor this. This is the function that I'm looking at. The floor of the logarithm. This is the largest power of 2 that fits in 9, the largest integer power of 2 that fits in 9. Now, you can see that expression here on line 18, where my number. So this function 2base, what it does is it takes in the base, it takes in the number. So in our example here, the base is 3, the number is 100. The result is what we're going to return. Okay. In other words, the result is supposed to be 10201. That's what needs to get printed to the screen. So the result initially is 0. We haven't done anything yet. Now, remember that when the process holds, when the process is fully done, our original number will turn into 0 because we've accounted essentially for every digit in that number. So when that original number becomes 0, we know we're done. So that is the condition on my while loop. I'm saying as long as that original number is bigger than 0, I still have stuff to do. And we'll see in a second that the body of the loop updates that original number each time through the body. It gets smaller, so eventually it will smaller but positive. So I mean smaller but non-negative. So eventually it will become 0, and when it does, the process ends. We return the result. Now, what is that result? So we start, n is 100, b is 3 in our example. We say, what is the highest power of 3 that fits in 100? The integer power. We get that power. Then, remember, we just saw in this example with the 5 that I needed to ask also about the coefficients. What was the highest coefficient of that power? So how do I know what the highest coefficient is? Well, if the highest power of b that fits in n is this variable power, then I can do integer division of my number 100. Here in this example here, where is that? Let's open the 100. Of my number 100, I'm going to take it and I'm going to integer divide by 3 to the highest power, in this case 4, right? And if I open Python here, we can see that in real time. If I take 100 and I integer divide by 3 to the 4th power, I get 1, because there's only one 81 that fits in 100, right? So this integer division gives me the coefficient that I need. So in this case, if I scroll below here, in this case, when we're turning 23 to base 5, I can say 23. Now that I've learned the highest power of 5 is 1, I can say, okay, if I take 23 and integer divide by 5 to the 1st power, where's the coefficient that should go in front of 5? And we see the 4. The second line in the while loop gives me my coefficient. Now that I've learned the coefficient and the power, I need to put this 4 here in the right position. How do I know what the right position is? Notice where I put the 4, because I learned that 5 to the 1st power was the highest power, and so I had put a placeholder for the 0 and then put the 4 in the 1st place. How do I do that in the code? How do I figure out exactly where the 4 should go? Well, notice that when I've learned what the power is, in this case 1, the largest power, I've essentially I've essentially put that digit 4 into the first bucket, counting starting from 0 from the right. So that's the 0th bucket, that's the 4th bucket. What this tells me is if I know what the power is, I need my digit to move to the left that many times. Now, moving a digit to the left is the same as just essentially putting zeros to the right of it, right? Let's go back here. So if I have 4 and I'd like to move it to the left, I could just write 40. Now I've moved it to the left by 1, 400, left by 2, 4,000, left by 3. So if I want the 4 to be moved to the left, this highest power of times, how do we move a number to the left? We multiply it by 10. That'll move it to the left once, but if I want to move it to the left twice, I can multiply it by power of 2 of 10. If I want to move it left 3 places, I can multiply it by a power of 3 of 10. That's 4,000, etc. So that's right here. See this coefficient? That's our 4. That's our 4. And I want to move the 4 left by by the same number of digits as the power. So in our example here, since the highest power was 1, I'm going to take the 4 and I'm going to multiply it by 10 to the first power. So 4 times 10 to the first power. And as you see, that gives me 40, which puts the 4 in the right position. So my result was initially 0. Now it's 40. I updated it to 40. Now, what did I do next? Next, I said, okay, we started with 23. We just accounted for 20. What is the remainder? That's the key word. I was interested in the remainder. Now, this line here is what gives me the remainder. It says, take that 20 that you just got, the 4 times the highest power of 5, right? That's b, that's my 5, that's my base, raised to the highest power, which in my case is 1. So take n, your 23, and look at the remainder after you've divided by that. So we just learned that if I take 23 and divide 5 to the first power, the quotient is 4, and the remainder that I was interested in is of course 3, the remainder. So I update n to this remainder, and then n becomes 3 in this case, which is not 0, so the loop starts over again. Now we say, okay, n is now 3. What is the highest power of 3 that fits in 3? Right, etc. And it goes on in the same fashion. Or highest power of 5, excuse me, we're in base 5 in the exam, is this problem. What is the highest power of 5 that fits in 3? And that's, of course, 0. So this power here will become 0. And just to test that out, let's ask the same question. Let me do the following. Let me load up this. So we'll go to desktop, we'll say Python, go to interactive mode, to base. Now we'll say, what is the log? So what is the highest power of 5 that fits in 3? Notice that gives me 0 point something, but I need the integer power, so I take the integer, and that'll give me, of course, 0. So if I go here and just look at the integer part, I see that it's 0. So the highest power is 0. So we know the 3 is going to go in the 0th place, right? What is the coefficient? What is the coefficient? The coefficient is, of course, 3, because 3 divided by 5 to the 0th power is, of course, 3. So the coefficient is 3. Power was 0. So remember, this expression tells us where that digit should go. Well, since the power was 0, 10 to the 0th power, that's the unit digits. So we know that our 3 is going to go in the unit digits, which is right here. So in the previous iteration, result was 40, but plus, now in the unit digit, we put a 3. And now we say, okay, what is the remainder after we divide? And that remainder is now, of course, going to be 0, and we're done. Okay, so um, so why is and that's the whole process. So one more time, we want to convert a number in the decimal system to base p. So we say as long as we haven't accounted for that number completely yet, as long as n is bigger than 0, we ask ourselves, what is the highest power of that base in that number? We find the coefficient that should go next to that highest power. We find the place, the place, the place holder in which we should write that digit, the place where that digit should go. And the way we do that is we take our coefficient and move it left by the appropriate power. We move it left the appropriate number of times. So if the highest power is 3, we're going to want to move it left 3 times. If the highest power is 5, we're going to want to move that coefficient left 5 times. And we put it there. Then we and then we look at the remainder after our original number n has been divided by that highest power of the base. And this loop continues, and of course n is non-negative, getting smaller each time, so eventually it's going to hit 0. And then we'll be done. So I hope that makes sense. I encourage you to play around with this function, but this is the procedure. If you go through this video of how I was doing this by hand, then the code is really a one-to-one port of this idea. I'm sure there are many more efficient versions, and if you look online, I'm sure you can find one. But my background is in mathematics, so every time I have to write some code that does something computational, it's just clearest for me to port mathematical ideas directly into code as opposed to using some bit manipulations or maybe some code optimization. So I hope that made sense. That is the video. Hope you enjoyed it. Have a great day.